Welcome to the next lecture. So in this lecture we will try to study the pulse shaping and why we need pulse shaping and what it is. So to motivate for pulse shaping techniques, we will first observe what is the effect of channel on the incoming pulses. So as you know now, binary ones and zeros will be represented by pulses, and till now we have been representing them by rectangle pulses. So this for 1 and suppose this for 0. But what will happen to these pulses when they are transmitted over any communication channel? So for that I will tell you one fact that how can we model a communication channel. Okay, so you transmit something, okay, some signal, suppose x of t, and the transmission medium right from your antenna to the transmit antenna to receive antenna, okay, that whole thing is a channel, and what you receive at the receiver is y of t. Now what can be this channel? So suppose it can be wire line, a telephone wire, right? It can be optical fiber, it can be a free space satellite channel, free space, or a typical wireless scenario where there are a lot of obstacles. There will be a lot of effects like scattering of waves, there will be diffraction and other sources. Whatever it is, I can think this of as a system, right? And I can think the input as what we transmit as input to the system and what we receive as output to the system. In fact, this modeling will be very useful for when we will study the fading and other channel modeling. So a channel is usually modeled as a linear but time variant system. Okay, and one of the important thing about channel is whatever channel you use, whether you use telephone line, optical fiber, or whether you use free space or usual wireless, we have limited bandwidth for channel, right? You cannot use any frequency on any channel. Suppose in wireline you can use low frequencies as in case of telephone, but if you transmit the signal at the same frequencies over the wireless channels, that it will not be transmitted. You need very higher frequencies for wireless communication. The reasons are several: antenna height and other things. Similarly, when it comes to satellite communication, there the channel requirements, bandwidth requirements are different. And in a nutshell, so most of the channels, practical channels, are band limited. So we have band limited channels. So how can we represent those band limited channels ideally? So if h of f is the frequency response of the channel, ideal band limited channel will be something like this, rectangular, right? Suppose if B is the bandwidth of this channel, so it means that this channel will allow the signals up to the frequencies of B bandwidth, okay, in this range. It will not, so if you transmit beyond this bandwidth, there will be huge distortion, you will not get the output. But here is now the fact, if we have this ideal channel and which has this we can say transfer function, or the frequency response of the channel is like this, it is a band limited channel. So this is h of f and it is a rectangular function. So I can write as f of f by b, right? And in fact here I can write suppose 1 by b, just an example. Now what will be its time domain? Its time domain equivalent will be Fourier inverse, and that will be sinc function. So to be more precise, if it is f by b, so that will be sinc of bt divided by bt, or just sinc of bt, so that actually means sine of bt by bt. Okay, I think that it will be this. Maybe some constant will be there, I don't exactly want here model it, but it will have sinc behavior. So here is the channel impulse response, time response. Okay, now to this channel, if you apply, now is my point, if you apply a rectangular pulse, this is your rectangular pulse, right? What will happen at the output of the channel? What will you receive at the receiver? See, here are some important points. How do you designate a symbol in wireless communication or even in general digital communication? So you designate symbol, you have a protocol that a symbol will be of some duration, suppose time t. Okay, so what actually we will be doing, we will be sampling at in such a way that, so we can sample it after every t period. What is the amplitude? So suppose this means 1 is transmitted, right? Then if next symbol is 0, so it means for a time period t, this will be the next pulse. Then again if next symbol is again 0, it means for next time interval t, it will be again negative. Then if next symbol is 1, so it means for next time interval t, it will be positive pulse, like that. Okay, now what will happen if you transmit this series of pulses over this band limited channel? Okay, we will not go into again some exact analysis, but just overall analysis. You are transmitting rectangular pulse over a channel which is represented by a band limited response, and in time domain the impulse response is sinc function. What is rectangle convolution? So rectangle applied to h of t. So see, if I represent by this pulse p of t, so the output will be h of t convolution with p of t. P of t is here rectangular. So if you just see rectangular convolution with sinc pulse, will have again a sinc behavior. Now see this, suppose this is the time, this will be time interval this t. So according to your protocol, your symbol is represented for time interval t. So from this time onwards is a turn of next symbol, right? But if you see, your symbol got now spread, it has these side loops. Now the next symbol will look like this. The next symbol will look like this. From this output of this channel, a receiver may not be able to get back, will not be able to get back these rectangular pulses. What happens? There is an interference between the symbol, and this is called inter-symbol interference. Okay, ISI for short. So this is what we want to avoid. We want to avoid inter-symbol interference. What should we do for that? So here is our usual pulse P of t. We want to do something called pulse shaping. Okay. See, what ideally we would like to do. Ideally, whatever channel does to the incoming rectangular pulse, right? We want to undo that. So for that, what we can do, we want to change rectangular pulse to some other pulse so that there is ideally no inter-symbol interference at the output. Although exactly zero inter-symbol interference is very difficult, but we can at least avoid interference. Okay, so that is what leads to pulse shaping. And the person who demonstrated first all these things is also Nyquist. Okay, so that is also called Nyquist inter-symbol interference criterion. So in next lecture I will be demonstrating that how to get this pulse criterion, Nyquist pulse shaping criterion. We will not derive again detailed mathematical analysis, but we will do empirical analysis which will be sufficient for our understanding of modulation for wireless communication.